Great. So today we're going to continue with the topic that we started last time, parameterized algorithms, and we're especially going to see more examples of this idea of branching that we saw last time. So I'm going to start with a problem that we also tried to solve last time, and that's feedback vertex split. So you remember that we said, given a graph, a feedback vertex set is just a bunch of vertices so that if we remove them, the graph will have no cycles. So feedback vertex set, I just the definition. A feedback vertex set in a graph G is a subset of the vertices, subset S, subset of vertices, so that G without S is acyclic. Or maybe I should write G minus S is acyclic. Now, last time we looked into this problem for tournaments, which are directed graphs where you have one edge between any pair of vertices. This time we want to look into this vertex for general graphs, but undirected ones. So I'm no longer assuming that I have an edge between every two pair of vertices. I'm just assuming that I'm given some graph G, but it's now an undirected graph. And also I want to allow loops and double edges and things like that. So I can have a situation where I have, for example, a vertex U, and I have an edge from U to itself. And I count this as a cycle too. So if I have something like this, I have to definitely remove the vertex U. And I can also have two vertices U and V and more than one edge between them. Maybe I have three edges between U and V. And of course, this also counts as a cycle. Okay, so what is the problem exactly? Well, the problem is feedback vertex set parameterized by solution size. So I'll give you as input just a graph G and some integer K, and I ask you, does this graph have a feedback vertex set of size at most K? So feedback vertex set parameterized by solutions. And let's say I have n vertices and m edges. And output is just, it's a decision problem. So I also give you some parameter K here. And the output is yes, if G has a feedback vertex set S, such that S has at most K vertices and no otherwise. Okay, and we want to solve this using branching. So recall the idea that we had last time for feedback vertex set on tournaments. The idea was that I have to kill every cycle. And in order to kill a cycle, I have to take one of the vertices in that cycle into my feedback vertex set. And then I was trying to really find cycles that were small. So in that case, I could always find triangles, and I could then always kill triangles. But in this case, I can't necessarily find a small cycle. It might be that when I want to do branching, I find a huge cycle. Maybe with, just imagine that this is a lot of vertices. And it might be that I don't have any arcs going in between, so that there is no smaller cycle in here. So if that's the case, and I want to do branching here, then I will have to say I want to kill this cycle, so I have to put at least one of the vertices on this cycle into my feedback vertex set. So I have n different choices, and if I choose a particular vertex, for example, if I choose this one, then I say I put this one in my feedback vertex set, and it kills all the cycles that included this one. But now I have to solve the problem on the rest of the graph, but my parameter decreases by 1. So I have to choose k minus 1 vertices in the rest of the graph so that all the cycles are killed. But if I want to do something like this, my branching tree would like something like this. So I start with graph G and parameter k, and then I branch into a bunch of other graphs, each of which have one vertex less than G, and the parameter is also k minus 1. But then again here, I have to branch a lot. Now, in my branching tree, I can say that as I go down the tree, the value of k decreases every time. So the height of this tree is at most k. But now my problem is that my branching factor can be large because who knows, maybe I have a cycle of length n. And then if that's the case, then my branching factor is n. So I'm spending n to the power of k time just in this tree. And at every node of the tree, actually, I have to find the cycle. So let's say that's a DFS. So this would be n to the power of k times n plus n. That's the overall runtime of my algorithm. And well, this is an XP algorithm, but it's not an FPT algorithm. So the question is, can I somehow choose these vertices that I remove in a more intelligent way so that I don't have to have a branching factor of n? I want my branching factor to be a function of k, ideally. Because if my branching factor is any function of k, let's say I have a branching factor of f of k, right? Then how many nodes will I have here? I will just have f of k to the power of k nodes, right? And this is fine as long as I spend polynomial time at every node. Then I will have this times some polynomial in n, and this is FPT. So that's my goal today. I want to find a way so that I have to try only polynomially many, only f of k many vertices each time where k is the parent. Okay. So let's talk about intuition a little bit. If I give you a graph and you want to kind of guess which vertices should be in a feedback vertex set, do you agree that vertices with higher degree should intuitively be more likely to be in my optimal feedback vertex set? Because if you have a vertex that has high degree, it's probably in some cycles, right? So ideally, what I want to do is that I want to say, find some function f and just take f of k vertices, but only take the vertices that have the highest degree. So let's say I sort my vertices based on their degree. So let's say my vertices are now v1, v2 to vn. And let's say that the degrees are decreasing. So the degree of v1 is more than the degree of v2, and so on, and the degree of vn. Okay? So if I sort my vertices like this, I would ideally like to take the vertices that have the highest possible degree. So if only I could find a good function f, then I could say that I take the vertices, the f of k vertices with the highest degree, and then I just try removing them. I just do this branching on those vertices, right? But this is like the general idea. We have to actually work more to figure this out. So having this general idea in mind, I'm going to do some other things first. So last time we saw that sometimes we can have rules that help us reduce the size of the graph. So let's just see what kind of rules we can come up with. So as I said, again, ideally I want to put vertices of high degree into my feedback vertex set. So let's see what I can do with vertices of low degree. The simplest case, if I have a vertex of degree 0, this vertex is just not going to be in my feedback vertex set because there is no cycle that goes through this vertex. But I can say the same thing about a vertex of degree 1. So if I have a vertex like this, and if this is the only edge going out of U, then there is no way that U can be in a cycle, right? Because any cycle has to start from U and it has to come back to U, and there is only one edge. So in other words, if the degree of a vertex is 0 or 1, I can just remove that vertex. So this is my first rule. If the degree of some vertex U is less than or equal to 1, then I take my instance, which was G and K, and I turn it into G minus U and K. And the parameter doesn't change because I'm not putting U in my feedback vertex set. Okay. What if I have a vertex of degree 2? What can I say about a vertex of degree 2? So let's say I have this vertex U, and it only has 2 neighbors. One neighbor is V, one neighbor is W. Would I ever put U in my feedback vertex set? Well, I can do that, but any cycle that goes through U has to go through both of these edges. So any cycle that goes through U also goes through V and through W. So if I put U in my feedback vertex set, it's always just as good to remove U from the feedback vertex set and put V into it, or to put W into it. So basically, it's never optimal to take U. I can always take one of its neighbors instead. So if I have a situation like this, I can again remove the vertex U and not put it in my feedback vertex set. But I have to make sure that since I'm not putting U in my feedback vertex set, by removing U from the graph, I shouldn't remove any of the cycles that used to exist, right? And the way I do that is that, again, I say any cycle that went through U also went through V and W. So I can just remove U and I can directly connect V and W together. So all of those cycles are now preserved. So I'm not changing any of the cycles, but I'm removing one vertex and making my graph smaller. Okay. So this is our rule number 2. I'm not going to write it in words, but basically this is what we're doing. Right? So if I have any vertex of degree 2, I remove it and I connect its neighbors together. Okay. But these were all cases where we were saying something is not going to be in our feedback vertex set. Are there trivial cases where I can say that a particular vertex has to be in my feedback vertex set? So one trivial case is what I already mentioned. If I have a loop from a vertex to itself, oh, sorry, we don't have directed graphs, it's undirected. So if I have a loop, this is a cycle, and this cycle only contains this one vertex. So I have to remove this vertex. And I have to put it in my feedback vertex set. What else? Well, let's say I have 2 vertices, and I have a bunch of edges between them. So maybe I have 5 edges between these vertices. Do I need all of these edges? So these edges, like any combination of them, any 2 of them, would give me a cycle between these 2 vertices. So all these edges are telling me is that I have to remove at least one of these 2 vertices. But I can just keep 2 of the edges and remove all the rest. And that's just the same thing, right? So I can take this and I can say I just keep these 2 vertices and 2 of the edges between them. Because the cycle is preserved. I mean, there are many cycles here, but they all get killed at the same time. So I can just take one of them. Yeah, but I don't care that much about these 2 rules. I mean, these are nice rules, but in my algorithm, I really need these 2 rules. Okay, so now, just as before, I would just apply all of these rules as many times as I can. Okay. What do I know after I apply all of these rules as many times as I can? I know that the degrees in my graph are going to be at least 3, because anything that had a degree of less than 3 was eliminated, right? And of course, if I apply these rules as well, I know that there are no self loops, and I know that the number of edges between any particular pair of vertices is at most 2. But this is the thing that I wanted to use. I just wanted to use the fact that all the degrees are at least 3. Okay. Now, I'm going to just give you the value for f, the function f that we were going to use, where we were saying that we're going to take f of k vertices. But again, when people were designing this algorithm, they just tried with f, and they did all the analysis, and at the end decided what to choose for f so that the analysis works. So I'm going to say that f of k is just 3k. So I want to choose my first 3k vertices. So these are the vertices with the highest degree. And I want to say at least one of them has to be in my feedback vertex set. Okay, so this is the theorem that I want to prove. I want to say, let's say my feedback vertex set is X. I want to say that if I take the intersection of X with my first 3k vertices, V1, V2 to V3k, then this intersection is non-empty, which means at least one of these vertices has to appear in my feedback vertex. Now, again, what happens if I can prove a theorem like this? Then I can do branching. I can just say that I take the first 3k vertices, and at least one of them should be in my solution. So I just do a branching. I just try putting V1 in the solution and recursively solving the rest. If that didn't work, then try putting V2 in the solution and recursively solve the rest, and so on. And so this would give me an algorithm that would have a runtime of 3k to the power of k, because this is our branching factor, and this is the height of the tree. And then hopefully at every node of the tree, I will also spend polynomial time, or hopefully even linear time, and then this would be my overall runtime. Okay? But now I have to prove this one. Okay. Let me see. Yeah. So what I want you to do first is to look at the graph G after we remove the vertices in X from it. So X was a feedback vertex set. So if I take G minus X, there are no cycles there. And so this graph has to be a forest. That's the definition of not having a cycle. So let's call it F, because it's a forest. So whenever I say F, I just mean G minus X. Now, what can I say about the number of edges in F? So what is the number of edges in F? If you have a forest on n vertices, how many edges can it have at most? N minus 1, right? Because if you have n vertices and you want to have a forest, you can at most have a tree, and a tree has n minus 1 edges, but you can't have more than n minus 1. So the number of edges here is going to be at most the number of vertices minus 1. But the number of vertices is, well, I had n vertices originally. I removed x vertices from it, and I also have the minus 1. So I know that when I remove x, the number of edges is going to be at most this much. Now, again, this goes back into our intuition that we have to remove vertices of high degree, because I expect that I have many more edges than vertices. But after I'm removing only a small number of vertices, only k vertices, my number of edges is going to become less than or equal to the number of vertices. So it's like I was really removing a lot of vertices of high degree. Okay. So What can I say about the sum of the degrees in F? Or actually, what can I say about the sum of the degrees of the vertices in X? So let's say I want the sum of every vertex that is in X, the degree of that vertex. And I mean the degree in the original graph G. Okay? Again, what I want to do here is to say that I need to take some of the vertices that have high degree. So I want to show that this sum is more than or equal to something. Because if I have a huge sum, then I can't just take vertices of low degree because I can only take k vertices. Okay, so here's what I claim. So this is just a claim and then I'll prove it. I claim that the sum over every V that is in my feedback vertex set of the degree of V minus 1 is greater than or equal to m minus n plus 1. Again, this intuitively makes sense. So I had m edges, I removed a bunch of vertices. Now I have these many edges. So it should make sense that the degrees should look like that. But let's just look at this graph F. So in F, I know that the number of edges of F is at most n minus x minus 1. So if I look at the edges of G, each edge of G is either an edge of F or it has one of its endpoints in X, right? Because that's the definition. I just took G, I removed all the vertices in X from it. So if an edge was removed, it had one of its endpoints in X. Okay, so I can try to use that and use this inequality. So here's the thing. If I want to take the number of edges in G, which is basically n, okay, what is this? This is the number of edges in F plus the number of edges that were removed because I removed X. Okay, but I want to somehow connect that to the degree of the vertices in X. Okay, so I can say that that's at most the sum of these degrees. Why? Because I'm removing a bunch of vertices. I'm removing X from my graph. Any edge either has both of its endpoints in X, and that's why it's removed, or it has exactly one of its endpoints in S, and that's why it's removed. So I just take the worst case and I say, what happens if all of the edges that were removed have only one endpoint in X and the other endpoint in G minus X? So in that case, the number of edges that I'm removing is just the sum of the degrees of vertices in X. So now I have this inequality. But I also had this one, so I can just put this into this. So I would get the sum of all the degrees in X plus, instead of this one, I just put this upper bound, n minus x minus 1 is greater than or equal to, and this one is just m. Okay, now this inequality is basically the same as this one. It's just that you have to take this n to the other side, this 1 to the other side, and here you have the sum of the degree of vertices in X, and then you have minus x. So you can just say that I'm taking the sum over vertices in X of degree minus 1. So this thing is exactly the claim. Nice. So I'm now going to use this claim. So let's remove this part, which was the proof of the claim. And let's talk about how I can use the claim itself. So now let's try to prove the main theorem. And again, I'm repeating the intuition over and over again here. I want to say that if I don't remove if I don't remove any of the vertices from these first 3K vertices, then I will have too many edges. So let me just try to count the number of edges. And let me just assume for a contradiction. So assume that I've taken none of these first 3K vertices. So assume that X intersection with this V1 to V3K is empty. And remember that X is supposed to be a feedback vertex set, and it's supposed to have at most K vertices in it. Okay, what happens if I have a situation like this? So let me just take this sum, but instead of taking this sum over X, let me take it over the first 3K vertices. So what can I say about the sum of degree of V minus 1 if this is taken over all the first 3K vertices? Okay, so I'm assuming that all of the vertices in my feedback vertex set X were at indices after 3K. So all of them have degrees that are smaller than the degrees of these vertices. And there are K of them. So this sum has to be greater than or equal to 3 times the same sum if I take it over X. Okay? Of V in X, degree of V minus 1. Okay? Because every vertex here has a higher degree than every vertex here. And also I have 3K vertices here, but I only had at most K vertices here. So this sum is more than 3 times this sum. Okay. But this sum was more than m minus n plus 1. So this main sum here is also more than 3 times m minus n plus 1. Okay, and I'm going to remove the proof. I just want that part. Okay. Now let's look at the same sum, but let's look at it on the other vertices. So I just want to find the same sum, but now instead of saying that I look at indices 1 to 3K, I say I look at indices 3K plus 1 to n. Okay? And again, for every vertex, I'm just taking the degree of that vertex minus 1. What can I say about this one? So again, I want to find a bound, and what I know about X is that all the vertices that I took in X were in this range of indices. They were in the range 3K plus 1 to n. So this sum is more than the same sum the same sum over the vertices that are in X. So this thing. I'm just dropping some of the indices there. That's fine, right? And again, this one was m minus n plus 1. Now, let's say I now finally want the same sum over all of my vertices. So if I just take the same sum over all of my vertices, so if I just take the sum over all vertices in V of the degree of V minus 1. Well, I can say that this sum is just the sum over the first 3K vertices plus the sum over the other vertices. So this is going to be greater than or equal to, here I had 3 times m minus n plus 1, here I had m minus n plus 1, so it's 4 times m minus n plus 1. Okay. Now, this is the inequality that I have. What does this sum on the left give me? So if I just take the sum of all the degrees, that's twice the number of edges, right? But I'm taking this sum, but I also have a -1. So this thing here is going to be 2m minus n, right? So this is the inequality that I got. 2m minus n is greater than or equal to 4m minus 4n plus 4. Okay. Let's try to find now a bound on the number of edges, m, based on the number of vertices, n. Okay, so I have 2m here. I can bring this 4m to the other side, and then I will have minus 2m. I bring this n to this side, and this is minus 3n plus 4. I multiply by -1 so that I have 2m is less than or equal to 3n minus 4. And finally, I just divide by 2. So m is less than or equal to 3n minus 4 divided by 2. Okay. And actually, I don't really care about that divided by 2 and so on. So what does this tell me? This tells me that I have very few edges, right? So what does, or actually, let me just, even this one tells me that I have very few edges. What does this tell me about the degrees of the vertices? So this is the sum of the degrees of all the vertices, and it is less than or equal to 3n. So there should be a vertex that has a degree of less than 3, right? Otherwise, the sum of degrees could not be less than 3n. So if I have a vertex whose degree is less than 3, that's a contradiction, because at the beginning, I could remove all the vertices that had degree 0, 1, or 2. I don't have any vertex that has degree less than 3. So this is already a contradiction here. And so we proved that no matter what, we have to take one of the vertices, one of the first 3K vertices that have the highest possible degrees. Okay. But again, this didn't hold without our pre-processing. We have to first do the pre-processing, which gets rid of all the vertices of degrees 0, 1, and 2. And then after that, we can say that we sort the vertices by degree, and we have to take one of the first 3K vertices. And now we have a branching that gives us a runtime that is 3K to the power of K times some polynomial. Okay, so this shows that feedback vertex set parameterized by solution size is also solvable in FPT time. So this is also an FPT problem. Okay, so now let me switch to a different problem. I just want to give you another example of branching. And I want to give you an example that doesn't really have anything to do with graphs or trees. Okay, I'll give you an example from strings. So let's say that we have two different strings, and both of these strings have the same length. So I have a string, let's call it S, which is like S1, S2 to Sn. Each of these is one letter. And then I have T, which is T1, T2 to Tn. So I can define a distance between these two strings, and I can say that the distance of S and T is just the number of indices where the characters in the two strings do not match. Okay, so number of indices I such that Si is not equal to Ti. Or I can just write it in a more mathematically correct way. Okay. So now we have a concept of distance between strings. The problem that I actually want to solve is that I'm given a bunch of strings and I have to find another string that is close to all of them. And I want to see if I can do that. Okay? So this is my input. My input is, let's say, m strings of length n. So I have m strings and each one of them has the same length. And let's call these strings, I don't know, let's call them sigma 1, sigma 2 to sigma m. And then I write sigma ij for the jth character in the I string. Okay, so I have this in the input, and I also want to have some parameter. So let's say I give you some parameter k in the input as well. And the output, you should basically find a string whose distance to all of these input strings is at most k. Okay, so a string, let's call that one, I don't know, delta, such that the distance from the string delta to every sigma I is at most k. And this holds for every I. Or if there is no such string, you should just say it's impossible. Okay. Or fail or impossible. Okay. Of course, you can again look at this as a decision problem that only gives you yes or no. But I actually prefer it if when the answer is yes, you can actually give me this string as well, not just say that the answer is yes. Okay. So let's just have like a pictorial representation here. Let's say this is my first string, sigma 1. This is my second string, sigma 2, and so on. And I have one last string, and let's say that this is sigma. Okay. First of all, what can I say about the distances between the strings in my original input? So suppose that the answer is yes. Suppose that there is a string that has distance at most d to any one of the strings in my input. So how far can sigma 1 and sigma 2 be? What is the distance between two strings that are already in my input? Well, it can be at most 2k, right? So first, I just go over all of the strings in my input, every pair of them, and I just find the pairwise distance. If I find two strings whose distance is more than 2k, I just say this is impossible, right? So now I can work with this because I know that the distance from every string to every other string is at most something that is bounded by my parameter. Okay, so I'm just going to try and create my solution string delta step by step. And what I do is this. I start by just setting my delta to be my first string. So let's say that delta is just sigma 1. Okay. Now, I can start comparing the candidate solution that I have here. It's not yet a finalized solution. I might want to change it with the strings that I have here. So yeah, delta is just sigma 1, so this distance is 0. But then I can take the distance of delta with sigma 2. Now, I know that this distance is at most 2k, right? But I have a problem if the distance is more than k. So let's say I just mark all the indices where this string is different from my current candidate delta. Okay. If I have more than k of these, then I definitely have to change one of these indices in my delta, right? And I have to change it to have the same character as here in this string, which was in my input. So I can just do a branching. So I know that I have at most 2k different places. And as long as I have more than k places, I have to choose one of them, and I have to change what I have in delta to what I have in sigma 2. Okay? So let's say that I choose index I. Now, how does my recursion work? Well, in my delta, I have to go to index I, and I have to say, I don't care what I have here, just turn this into what I had there. So turn it into sigma 2I, right? And then I have to also make sure that I would not change this again ever after this, because if I change it again, then I'm again getting a larger distance between sigma 2 and delta, and I don't want that to happen. So I change this index I, and I also keep track of a flag or a Boolean variable or a check mark here that just says, this is fixed, I will never change this in the future. Okay, and then I just continue like that. So every time I have now kind of a different problem. Instead of just saying that my input is m strings and so on, I can say that I also have some string delta in the input. And this string delta has a distance of at most 2k to any one of the other strings. And I can also say that some indices in this delta are fixed, and I can change those. And then my output is just going to be which indices of delta should I change and to which values, right? So now looking at it like that, how does my tree look like? How does my branching tree look like? So I will have an instance that has sigma 1 to sigma m, and it has some delta, right? And of course, it has some k. Now, first of all, I just take delta, and if the distance from delta to any one of the other strings here is more than 2k, I just say no. Otherwise, I just go through this process. But what is my branching factor? So in how many different indices can I do something like this? In how many different indices can I say that at index I want to put something from my input string, and then I'm not going to change this index anymore? At most k, right? Because the distance from delta to this sigma 2 or whatever, sigma j, was at most 2k. And as soon as the distance becomes less than k, I'm happy. So if I have more than 2k indices here, sorry, if I have more than k indices here, I can just take the first k ones or first k plus 1 indices and then say that I have to take at least one of these indices and fix it. So actually the branching factor is, to be very precise, k plus 1. Okay, but after I do this, then my parameter k decreases because k is the number of places that I can change in delta. And I've changed this index, and I'm saying that I will no longer change this index anymore. So when I'm doing this branching, at any of these children, I will have some instance, and the instance has the same size, but now I have parameter k minus 1. So my branching works, and let's do an analysis now of the runtime. So this is a branching tree that has depth k minus 1, but at every point it branches to k plus 1 children. So the number of nodes is going to be OK plus 1 to the power of k minus 1. Okay. Sorry, k plus 1 to the power of k. Right, but how much time do I spend at every one of these nodes? So how much time do I spend to find an index that I have to change? Well, in the worst case, I take this delta and I go over all of these sigma strings, and maybe the distances are fine with all of them until I get to the last one. And then the distance is not fine there, the distance is more than k, and then I have to go through this whole thing. So I have to compare each one of these strings with my string delta. These strings, there are m of them, each has length n, so that would just be m times n. Okay. Again, what I really care about here is that I got an FPT algorithm, because this is some function of k, this is some function of my parameter, and I don't care how big this function is because I'm assuming that my parameter is small. And then this part is polynomial. This is basically the size of our input, right? So I can say this is linear time, because if you think of the size of the input is also m times n. So I got a linear time FPT algorithm. Nice. So now I'm going to switch to yet another problem, and I'm going to actually show you a different technique. So we're not going to talk about branching anymore. Now the next problem is the problem of longest path. So I give you a graph, and again, let's say that this graph is undirected and unweighted, and I ask you for the longest path in this graph. And by a path, I mean, of course, a sequence of vertices and edges such that no vertex is seen more than once in this sequence, right? So I can't go back here and then continue. That's not a path. But if I just have distinct vertices, okay. So if I just give you a graph and ask for the longest path, that's an NP-hard problem. Can you see why? Because if you look at the classical problem of Hamiltonian path, that's a special case of longest path, right? So Hamiltonian path just asks you if I have a path with n vertices. But of course, if I have such a path, then it's the longest path. So if you have a solution for longest path, you have a solution for Hamiltonian path, and Hamiltonian path is NP complete. So longest path is NP hard. Okay. But I want to somehow parameterize this. So of course, I can just parameterize by the lengths of the paths. So again, the problem that I'm looking into is going to be longest path parameterized by solution size. And my input is just a graph G and some parameter K. And the question that I have to answer, or my output, is whether G have, does G have a path with K vertices? Okay. So let's just try with naive ways first. Let's just see what is the simplest algorithm that comes to our mind. Well, we can do some sort of a backtracking algorithm, right? So I can start at any particular vertex, let's say vertex 1, and then I can just try to go to another vertex, take an edge and go to another vertex, and so on, until I can no longer go anywhere. And then I would just backtrack and try from this one. Maybe then I can go somewhere. And I'll just continue this. So it's very similar to a DFS, but the difference is that you don't really mark your vertices as being seen, right? So in a DFS, you would see every vertex at most once, but here the only thing that you have is not to see every vertex at most once, it's just to have every vertex in your path at most once. And that's why this takes much more time than DFS. This doesn't take polynomial time. Okay, so what is the runtime here? How much time does this backtrack algorithm take? It's not polynomial, but can you find the bound? Well, it might be easier if instead of backtracking, we look at this as a dynamic programming. So let's say I do a dynamic programming like this. I say I have a dp variable for any sequence of vertices. Okay, so for any sequence v1, v2 to, let's call it vr, I say that their dynamic programming variable is 1 if this sequence is a pass. And it's 0 if this sequence is not a pass. Okay, and then I can compute this by dynamic programming, right? Because I can just check that the first r-1 vertices are a pass, and that the vertex at index r-1 has an edge to the vertex r. So I just need to see how many sequences I have. And the number of sequences is actually quite large. Right? So if I look at sequences of length r, I basically have n to the power of r of those sequences. And then I'm looking at sequences of every length. So the total number is r from 1 to n to the power of r, which I can say is at most n to the power of r plus 1. Sorry, n to the power of n plus 1. Right? Because all of these terms are at most n to the power of n, so this is n to the power of n plus 1. Now, this is not very useful because this just, yeah, of course, it shows that the problem is decidable. There is an algorithm that solves it, but it's a terrible algorithm. Can we do better than this? Well, when I'm doing this dynamic programming, I really shouldn't care about the order in which I've seen these vertices, right? I only care about which vertices have I seen and what is the last vertex that I've seen. Because if I have some other vertices in my path, I can't go to those vertices anyway, and it doesn't matter in which order they appeared in my path. So maybe instead of this, I can have a different kind of dynamic programming. And maybe I can say that for every subset of my vertices and for every particular vertex, so for every S and V, I define a dynamic programming variable that looks like this. And this is 1 if there is a path that sees all the vertices of S and ends in V. And let's also assume that V is also in S. Okay? And it's 0 if there is no path that sees all the vertices in S and then ends at V. And again, we can compute this quite easily, right? So if I want dp of SV, it's just that I know that S is the set of all the vertices in my path and V is the last vertex. So I can just try to find the second last vertex. So let's say I have this vertex V, and let's say its neighbors are U1, U2 to UT, right? So the second last vertex had to be one of these. So I can just say that dp of SV is, well, assuming that I take UI, I have to go from S minus V to UI. And that's it. And then from UI, I can go to V. So, and then I have to take the OR over all UI. Okay, so now how many DP variables do I have? Well, I have 2 to the power of n different choices for S, and at most n different choices for V. So the number of variables that I have to compute is at most 2 to the power of n times n. Right? And for each of them, I'm spending at most n time. So this algorithm is at most O2 to the power of n squared. So you see, we just discarded some extra information that we didn't need, and our runtime improved. So from n to the power of n to 2 to the power of n. But we're not yet using the fact that we're not really looking for the longest possible path. We're just looking for a path of length k, and k is small. So that's our parameterization. So what happens if I apply this parameterization? Well, that basically means that here, when I'm considering subsets, I have to consider subsets of size at most k. Right? So now the number of different values that I have to look at for S is going to be n choose k, right? But I have to also take subsets of smaller size. So n choose k plus n choose k minus 1 plus n choose k minus 2 and so on. Okay? So, but that's at most, assuming that n is much larger than k, that's at most something like k times n choose k. Right? So now my overall runtime is k times n choose k. Now, how about this part? So this part, whenever I was looking at the vertex, I had to look at all of its predecessors, right? But since I'm looking at since I'm looking at subsets of size at most k, I have k vertices, and each of them, of course, can have n predecessors. So my overall runtime is now k squared n choose k times n. Okay, and this is something like, yeah, k squared n to the power of k at most, and this is n, so n to the power of k plus 1. So this is an XP algorithm because we have a function of k, we have k plus 1 in the degree. So I don't like this. I want to find an FPT algorithm. Okay. What is the problem with all of our dynamic programmings here that is really causing us to have to do so much work? The problem is we have to keep track of this set S. We have to keep track of all the vertices that we have seen until this point so that we don't see them again. Right? So if I can somehow find an idea where I don't have to keep track of so many different histories of what I have seen, then I would be able to really reduce the overall runtime. So here's one idea. Let's say I just take k colors and I color all of my vertices randomly. And then when I want to find a path of length k, I say that the path should always start at color 1, then go to color 2, then go to color 3, and so on. And it should end with color k. So I'm using some randomization. I'm randomly coloring my vertices. And then instead of just saying that I want a k path, a path with k vertices, I say I want a path that has exactly these colors, 1 to k in the same order. Okay. So now would it be easier to answer this question? So if I give you a graph that is colored like this, and I ask you, is there a path that looks like that? How much time does it take to answer that question? So I can take any vertex of color 1, and I can just do a DFS from that vertex. But the rule is that when I'm doing a DFS, I only go to the next color. So you can think of it like this. I have a bunch of vertices of color 1. Let's call them C1. I have a bunch of vertices of color 2, color 3, and so on, and until I have color K. Right? I have to start here. I have to take an edge that goes here, then another edge that goes here, and so on, until I get there. So I can just do a DFS starting at a vertex here, but I ignore all the edges that go anywhere but to the next color. And in my DFS, I only go to the next color. And here again, I continue the same thing. And if I can reach a vertex here at color K, then I have found a path with K vertices. And of course, I have to do this for every vertex of color 1. I have to do a DFS from any one. So I'm doing at most n different DFS operations, and that's going to take me order n squared plus nn, because each one of the DFS operations took n plus n. Okay? But now I have to do an analysis of my randomness, because my original input doesn't have any colors. I'm just saying that I take every vertex and I randomly assign it a color between 1 to K. And I do this uniformly at random. So now I have to say, what is the probability that my algorithm succeeds? So suppose that I have some path of length K and it doesn't have any colors initially, but I'm randomly giving colors, right? But then my algorithm will succeed in finding this path if the colors that I gave were exactly 1 to K. Okay? Or maybe the other way around. Maybe 1 was given here, then 2, and so on until K. So the probability that my algorithm succeeds, assuming that there is a solution. Of course, if there is no solution, my algorithm would not find a solution and it would say no, right? But the probability that I get success according that a solution, assuming that a solution exists, is how much? Well, every coloring is equally likely, and 2 of the colorings will give me the solution. But how many different colorings do I have for these K vertices? K to the power of K. Okay? So if I just run this algorithm, the probability that I succeed is at least 2 over K to the power of K. But as we've seen before, we can just repeat this algorithm with different choices of randomness, and this will increase our probability of success. And specifically, if I want my probability of success to be some constant number, I can just repeat this K to the power of K times, right? So I get this same runtime times K to the power of K. And then my success probability is a constant. And if I want to succeed with high probability, if I have a constant probability of success, and let's say I want to have an n-1 over n probability of success, so at most 1 over n probability of failure, we've seen that we can just repeat the same algorithm log n times. So I can just multiply this by log n, and this is my final runtime. And with high probability, my algorithm would find any path of length K. Okay, is this FPT? Yes, because this part and this part are polynomial in the size of the input, and this is just some function of K, and I don't really, again, care about this function. But when I say I don't care about this function, I don't care about it in terms of finding an FPT algorithm. So in the definition of FPT, it doesn't matter what function we have here. But in practice, of course, K to the power of K might be large for you. So it depends on what kind of graphs you're really using in practice. So if K is, for example, 20, then K to the power of K is going to be a large constant factor. So the next question is, can we do better than this? So this was the idea of color coding. I just gave a color to every vertex at random. But do I really need to have colors, C1 to Ck? So how am I using these colors in my algorithm? The way I'm using them is just for limiting the edges that I can take in my DFS. Right? I'm saying do a DFS starting from color 1, and every time you are only allowed to take the edges that increase your color. Right? Now, what if instead of K colors, I just use N colors? So I give any one of my vertices a different color. Or another way of saying this is that I just randomly order my vertices. I just give my vertices some random order, and I always say that starting from any vertex, you can only go to larger vertices. You can never go back to smaller vertices. This is also enough for solving the problem that we had here. Our problem was that we had to keep track of the history of the vertices that we've seen in the past. But if my path can only go from smaller vertices to larger vertices, then I don't need to keep track of the history, because everything I've seen before is smaller, and everything I'm going to see in the future is going to be large. Okay? So now I'm changing my randomized algorithm, and I'm saying each time, just assign a random number to each one of these vertices, a random number between 1 and n, and only consider paths in which the numbers increase. Now, I can again do the same thing that I was doing before. I can do a DFS from every vertex, and I can just see how far I can go increasing the path. Okay, but so I have the DFS part. What is the probability of success? So if I have a path, and this path has k vertices in it, I would succeed in finding this path if the weights that I assign to these vertices are in order. So they should either be increasing or decreasing, right? So now my probability of success, assuming that a solution exists, is going to be 2 over k factorial, right? Because I'm assigning random numbers to each one of these vertices. So there are k factorial different orderings that I can have on those numbers. And all of those orderings are equally likely. But 2 of them would work for me, the increasing order and the decreasing order. So my probability of success, if a solution exists, is at least 2 over k factorial. Okay. Now, the only difference is that I had 2 over k to the power of k before. So in order to get constant probability, I had to repeat the algorithm k to the power of k times. But now I have to repeat it only k factorial times. K factorial is much smaller than k to the power of k. So my runtime just becomes k factorial here. And I don't need k to the power of k anymore. Okay. But can we also make the polynomial part faster? So here I'm just doing a DFS from every vertex. Can I maybe do something smarter instead of just doing a DFS from every vertex? Because the DFS is now taking n times n plus m time. But if I have an ordering over all of my vertices, so let's say I put my vertices in a line in the order of their number or color. So I have vertex 1, vertex 2, vertex 3, all the way to vertex n. And I know that I can only take edges that go from left to right. So I just process all of my edges and I remove all the edges that are not like that. Or actually, it's the same as saying I give a direction to all of my edges. So for example, if I had an edge from 1 to 3, I give a direction like this. I can go from 1 to 3, but I can't go back. So all of my edges are now directed from left to right. So this is a directed acyclic graph. I can't have a cycle because I'm always going to the right. And I want to see if this directed acyclic graph has a path of length k. Okay, how can I do this? I just do dynamic programming again. And for each one of my vertices, I just keep track of the longest path, length of the longest path that ends at that vertex. So I just say LP of I is the length of the longest path. And okay, when I'm saying length here, I mean the number of vertices, not number of edges. So length of the longest path ending at vertex I. Okay. Now, can I compute this? Well, of course. So this part now. Let's say I take my vertex I, and I want to find the longest path that gets to vertex I, that ends at vertex I. I just think about who's going to be, which vertex is going to be the second last vertex in that path. So I take all the vertices that appear before I and have an edge to I. Okay, so let's call this U1, U2, maybe up to UK. Well, no, I've already used K. So U1, U2 to UT. Okay, and then the longest path to I is just the longest path to one of these predecessors plus 1, because there is one extra vertex, which is I. And of course, I have to take the maximum of this over all of my predecessors. Okay, so that's a simple dynamic programming. But how much time does this dynamic programming take? So the time I spend at vertex I is proportional to the number of predecessors of I. So that's the number of edges coming into I. So my total time is just going to be proportional to the total number of edges. So, and of course I have n variables, so my overall runtime is O n plus n. So I got a factor of n out of there. So now our runtime here is going to be n plus m times k factorial times log. Can we do even better? So just think about what we were doing when we had no parameter. First, we said we just keep track of the whole history. Then we said instead of keeping track of the entire history, we just keep track of the subset of vertices that we've seen. Now we can do the same thing after color coding. So in the algorithm that I had that assigned k colors to the vertices, I then said that I want to see all these k colors in order. But what happens if I just say I want to see all the k colors, not necessarily in the right order? Okay. So now, let me fix this one. I want to extend that dynamic programming. So I say my first step is to just assign colors to all of the vertices. So step 1, randomly and uniformly assign the color. And the color is going to be between 1 and k to every vertex. And then in step 2, I'm going to ask, is there a path that sees all of the colors? And I don't care about the order. let's call that a colorful path. So is there a colorful path? Which means a path that sees all of the K colors. Okay. How can I solve this one now? So what we're doing here is that we're saying our history matters. It matters which colors we've seen, but the order doesn't matter. So I'm going to use something very similar to the non-parameterized case when we were saying that the order doesn't matter. So I'm going to define another dynamic programming. And now I'm saying that, let's say I have some set of colors C, and let's say I have a vertex V. And I ask, is it possible to have a path that ends at vertex V and sees exactly the colors in C? And of course, each color has to be seen exactly once. Okay? So for every vertex V and every possible subset of colors, every C that is a subset of 1 to K, I want this dynamic programming. I want to say, is there a path ending at V whose colors are exactly the set C? So, okay, those colors are C. Now, how do I compute this dynamic programming? Well, first of all, if V has a particular color, for example, let's say that vertex V has color 1, then I know that dp of 1V is going to be true, because that's just the single vertex. Yeah. So that case is easy. That's the base case. But how do I compute dp of CV in general? Well, first of all, the color of V has to be in C. Because if the color of V is not in C, there is no such path. Now, if the color of V is in C, then what do I know? I know that I have this vertex V, and it has some color. Let's call it small c. And it has a bunch of predecessors, or a bunch of neighbors, let's say. Okay? I have to choose one of these neighbors such that I have a path that ends at that neighbor, and the colors that are used at that neighbor have to be the colors here minus the color that was used at V. Okay? So if the neighbors of V are, let's say, W1, W2 to WT, then dp of CV is just going to be dp of C minus the color of V, which I showed with small c, sorry about that. And, well, I have to go to one of these neighbors, so WI. And I take this or over all WI, so or I from 1. Okay. Nice. So now I can compute this dynamic program. But I have to analyze my runtime again. So first of all, what is the runtime of this dynamic programming? I have 2 to the power of k different values for C. And for each of those 2 to the power of k values, I'm basically spending n plus m time, because if you consider a fixed C, I'm taking every V and every predecessor, so I'm looking at every edge exactly once. So that runtime is just 2 to the power of k times n plus m. But this is the runtime for solving this part. But we have to also, again, talk about our probability of success. So I'm randomly assigning a color to every vertex. What is my probability of success? Let's say that I have a path of length k, again, because I want my probability of success only if this path exists. So probability of success, assuming solution exists. Okay, so how many different colorings do I have? Again, I'm just randomly coloring each one of the vertices with one of k colors. So I have k to the power of k different colorings. But how many of the colorings would give me a solution? As long as I assign different colors to these vertices, I'm fine. And my step 2 algorithm would find this path. So in how many ways can I assign different colors to these k vertices? Well, that's just going to be k factorial. So now my probability of success is k factorial over k to the power of k. So if I want my probability of success to be a constant, I have to just invert this, and I have to run my algorithm k to the power of k divided by k factorial times. Okay? And then again, I can have another log n factor if I want it to succeed with high probability. Now, this is good because there is this thing called Stirling's approximation, which basically says, let me see. Yeah, Stirling's approximation says that k factorial is more than, okay, I have to write this. Square root 2pk k over e to the power of k, e to the power of 1 over 12k plus 1. Okay, this is Stirling's approximation, but I don't care about this part. I don't care about this part. The only thing that I really care about is that k factorial is more than k over e to the power of k. Okay, so this part is going to be e to the power of k. Or maybe some constant times e to the power of k, right? So now I have, yeah, this part is going to be e to the power of k. I have 2 to the power of k here. So I just get a total runtime of 2e to the power of k times n plus m times log n. And now this is much better than all of the previous runtimes that we had. Okay, that's it for today, and I'll see you next week.